Hey gang, and welcome to the Worksheet Solutions Walkthrough for the worksheet Grignard Practice and Synthesis. If you're new to Worksheet Solutions Walkthroughs, they go a little bit like this. Maybe you've seen the instructional video, about Grignards and synthesis with Grignards. You did the worksheet, but you were looking for more answers. Well, you are in the right place. In this video, we're going to tackle this worksheet problem by problem, and I will show you how I arrived at the answers I provided, as well as my thought process behind them. So let's do it. In problem 1, I wanted to keep it kind of light and breezy because this worksheet is really geared at synthesis. However, I like these problems just because I feel like they get the retrosynthetic analysis, brain fluids going, right? I do have one problem where it's a complete reaction, but I like these three because it's more of go from the end, provide what's at the beginning, okay? So in problem 1, the way to go about these, when you are given a Grignard product and you need to provide the reactants, locate where the alcohol was produced, right? It's that carbon that's kind of the connection point. You know that carbon was your carbonyl carbon. So what I like to do is I locate that carbon and then I break a bond right there. So it's this carbon as well as this carbon that were meshed together, right? So I know this was my carbonyl portion, which is 2 carbons. So I know that that was this right here, and I need to now provide my Grignard. So I can see that it's these 4 carbons right here, and I'll make sure I carry over my dot. I'll even carry over my asterisk. Oh, I'm going to give myself a little bit more room. You'll see why. And then I will provide an Mg. There's a really wrong way to write this. I'm just going to do MgBr like that. But the point being is that find the connection point, make a cut, grab those molecular scissors out of that drawer you put them in, and there we go. All right, so in problem 2, we have a conventional complete the reaction problem. So even draw the curved arrows. I could do this right here, and then assume what workup is going to happen. So what I'll go ahead and do is I will dot this, I will asterisk that. I will I'll do this in blue. I'm just going to go over here to give myself some more space. I know my OH is right here. I have my dot. And then I can draw a line, and I'm confident that I am now attached to my asterisk carbon, which is just the first of, 3 carbons. So that is a valid product right there. All right, moving down to here. And I'm realizing I just drew this incorrectly, so let me fix that. Looked a little bit weird. Okay, there we go. So it's at this point that I can see my Grignard product right there. So what I can go ahead and do is, this is my carbonyl carbon, I can make a cut right here. I could say this is my Grignard right there, these 2 carbons. So I could then draw a Grignard like this. I don't know, MgCl. Why not? Doesn't always have to be bromine. And then I can draw my cyclopentanone, which was the carbonyl that was attacked. Last but not least, we can see down here, this one I like. It's a little bit, it's kind of, it's weirdly can stump people, but this carbon was attacked. We were attacked by this carbon right here. So this is a case where we had a 1 carbon carbonyl. So we had formaldehyde, right? That is my dot carbon. And then we just had isopropyl Grignard as our nucleophile. Okay, gang, this worksheet is all about the synthesis, and this video could get super long if I actually do each individual one. So I will throw the synthesis problem up here, and we will step from the end to the beginning, having everything drawn out just so this video isn't obscenely long, all right? So let me erase this, and we'll do some synthesizing. Okay, gang, problem 2 and letter A. So in this problem, remember the first rule, at least in my opinion in synthesis, is count your carbons. See what you're given, what's in the product, and at least figure out what of your starting material will you be using, how much of each. So in this product over here, we can see we have 6 right here in the ring, 7, 8, 9, 10, and over here, 6-membered ring, 7, 8, 9, 10. So, and I think you can even, with this example, right, I wanted to start off a little simpler. We can see we're going to need 1 of the ring and 1 of the butane from our starting material. Okay, So clearly we know this, we can see this is a Grignard reaction, right? We've stitched two carbon pieces together and we've produced an alcohol, right? That's the definition of a Grignard reaction, right? That's the functional group, or the aftermath we expect. So what we need to do, remember, start at the end, work backwards. So don't get overwhelmed. The first thing you need to do is just figure out what was the carbonyl that was attacked and what Grignard attacked that carbonyl, right? Make a cut and step it back, okay? So, just like we did in the problems before, find that carbonyl carbon, right? It was this carbon right here. Then what you can do is you can make a cut. So this piece is the carbonyl, this piece was the Grignard. Specifically, it's this carbon right here that was the Grignard. So, in stepping that back, I hope you can see that this 6-membered ring with the alcohol was cyclohexanone, right? It's no surprise that this is the dot carbon right there. And in looking at the Grignard that I've drawn, I hope you can see, okay, 1, 2, 3, 4, and it's 1, 2, 3, 4. And you can see that this asterisk carbon is the same carbon we see right there. This is sec-butyl Grignard, right? Common name and still coming back. So, at this point, you really have two problems. And they're much smaller and they're much more easily digestible, right? Easy to attack than the one we started out with. So let's take it one at a time. Let's go the top route. So we need to work this all the way back to cyclohexane. So what is one way? And remember, starting out, the tools we have are put a halogen on. And then from there, right, we can do, SN2, SN1, right, and all that stuff. So let's try to simplify this as much as possible. So how can we produce ketones? What's a reaction we know? Well, they come from oxidized alcohols. So if we step this back, and at this point we could either use Jones or PCC, right? Or, doesn't matter, either or. This would then allow us to step back to an alcohol. So we're an alcohol on a secondary carbon. So I know, right, I know you saw this, but if I cover this up, stepping this back one, right, we have, we could then put a good leaving group on, right, either bromine or chlorine. Well, going from here to here, we really have two options. Would we do this through sodium hydroxide, SN2, or would we use SN1 with water? And remember, it's a secondary carbon. We don't have to worry about any carbocation shifting, but hydroxide in that secondary situation is going to give us a weird mix between elimination product, E2, and SN2. But if we do SN1, we're going to get this minuscule amount of E1 product that doesn't even matter. Our synthesis is better off and more accurate if we do this with SN1 to go from this secondary alcohol to a secondary alkyl, bromide, chloride, what have you. And we can easily put this on by doing free radical bromination. Day one, baby, right? Our first reaction. So now going down to here, so how do we make Grignards, right? We need to move this all the way back to bare bones butane. Well, we have our Grignard here. The last thing we do is we prep a Grignard with elemental magnesium. You may include this THF if that's what you do in your class. If you do, put it there. If not, don't worry. That will give us, an alkyl bromide, an alkyl chloride. And I did choose bromine at first. And I would show you that even if you did chlorine, you'd see why this bromine's the better choice. We need to put a halogen on a secondary carbon, right? If we were to Cl2 and light, we would have a hefty bit of this product. So bromine is the better choice here because you would get so much more higher yield of this secondary product than you would with chlorine. So I think this is a good synthesis. So on to letter B. In letter B, we see we are given propane and isobutane, and we have that product, that alcohol, over on the right. So of course, this is the Grignard synthesis worksheet. So no surprise, we see a alcohol in our product. We see carbon pieces stitching together, evidence of a Grignard reaction. Okay, so if we take a look and count our carbons, we have 3 and 4, so that is 7. And over here, 1, 2, 3, 4, 5, 6, 7. And I think you can maybe even see them out, but one of each is what the doctor ordered for this synthesis. So if we take a look, right, the first thing we need to figure out is how do we take this problem and break it into two mini problems, right? We need to, with acidic workup, step this back to draw the carbonyl we attacked as well as our Grignard. So I hope you're seeing this was the carbonyl carbon, right? It's directly attached to the alcohol. That was the carbonyl. So at that point, I think you can see if we made a cut, 1, 2, 3, 4, if we made a cut right here, I didn't do a great job of explaining this in the last video, or the last take, but this gives us this piece, and that leaves this 1, 2, 3 piece right there. You want to make cuts that are convenient for you, right? Don't make anything that's going to fragment or shard or make you have to do anything crazy. All right, so I think you can see that if we have 1, 2, 3, 4, if we were to draw a 4-carbon carbonyl like this, an aldehyde, well, that is the carbonyl we attacked. And up here, we would see this asterisk carbon right here. That was the Grignard. So it's on that secondary carbon in isopropyl Grignard. Okay, so let's tackle this first. So we have to go all the way back to isobutane, so we need to simplify this. So how do we get aldehydes? Well, we can oxidize primary alcohols. Not with Jones, but with PCC, right? Because PCC is more mild. Jones would take it all the way to the carboxylic acid and overshoot the aldehyde. So if we step this back with PCC, that is good for us. So with this primary OH, so I hope you're seeing why I had those questions on the alcohols worksheet, right? On, oh, should we use SN1 with water or SN2 with hydroxide? With a primary alcohol, that's a great candidate for SN2. So if we were to step this back, right, we would need a good leaving group on that primary alcohol. We could choose chlorine, but we would do this through SN2, not SN1, right? We don't want to make a carbocation on a primary carbon. That's going to not really happen. It's going to be too unstable to form. So you can use sodium hydroxide, and if you want to flex a little bit, you can include a polar aprotic solvent like DMF. This is completely optional, but you could do it if you want to. I didn't include it in the solutions, but you paid for extra, folks, so I'm giving it to you. And last but not least, right, we need to put a halogen on this primary carbon. Our two options are bromine and chlorine, and I know bromine's more selective, won't go there. Bromine's going to 100% go here, so we need to do free radical chlorination to get that primary halogen on there. Okay, now up top. This is a little bit faster. We have a full Grignard reagent, so let's set that back with magnesium. Again, THF is optional. At this point, right, it's the same deal. You might be thinking this, you don't know if that's bromine or chlorine, but you see it's on a secondary carbon. That's the more selective position. So you would go with bromine, knowing it's going to go there essentially 100% of the time when you do the halogenation. Wraps up the synthesis with a nice bow. Okay, letter C. Okay, gang, so in letter D, we can start off by counting our carbons. We see a ring of 5 and 1, 2, 3. And if we take a gander at our product, we see a ring of 5, 1, 2, and 3. So it looks like one of each here will give us our product over there. Okay, so one more of these, what I would call simpler problems, and I promise you I did this right off the bat to make sure you got the, like forming the Grignard thing down and getting the second, ketone and taking it back all the way down, and aldehyde all the way back down. So if we take a look here, business as usual, so we see this is a Grignard product that we need to establish, but first and foremost, we see that is the carbonyl carbon that once was. So if we make a cut right here, I think you'd see 1, 2, 3, that looks pretty convenient, and then the ring, and that looks pretty convenient too. So if we step this back with acidic workup, because we see we have OH, we would have a 3-carbon carbonyl, and I think you can identify the dot carbon would be that carbon right there. It's an aldehyde, and our Grignard is going to be the cyclopentane Grignard right there, pentyl Grignard. So it's on that secondary asterisk carbon. So stepping these back, business as usual. Once we've done that, we've really done ourselves a favor and given ourselves 2 smaller problems. Let's start low first. The Grignard's always faster. So if we step it back, right, we know we have the last step in making a Grignard is providing the magnesium. So one step back, that leaves us with our halogen, bromine, chlorine. I went with bromine. And to take it back to cyclopentane, just a little free radical bromination ain't never hurt nobody. So that takes care of that. And if we go up top, right, how do we, create aldehydes with the knowledge we have right now? using PCC to oxidize a primary alcohol to an aldehyde. So stepping this back, with PCC we get that primary alcohol. Now it's going to be, how do we generate this OH, which is primary, right? You should be thinking SN1 or SN2, and SN2 should be prevailing in your brain. So we could step this back with NaOH or KOH. OH better be there, OH minus, and for the flex, polar protic solvent, acetone, DMSO, DMF, whatever. You could step that back to, here it will matter, right? Because we will have this, and to step this back to propane, we want to chlorinate, not brominate, because we know bromination would end up here in high yield, not the primary position that chlorine would gravitate towards. Okay, gang, so these last three, we're gonna crank up the temperature, so let's go. Okay, gang, letter D. So in this problem, counting carbons right off the bat is gonna be very crucial. So we see in our given material, we have 1, 2, 3, 4, 5, right? So piece of 2, piece of 3, 5, 2, in total, and 1 of each. Now if we look over here, we have more than 5. We have 1, 2, 3, 4, 5, 6, 7. We have 8 total carbons. So in thinking of the combinations we can make over here, preliminarily, I think it's a good idea to say we use 2 of the propanes to make 6, and then we use 1 ethane total as our carbon source to get 8. But what we can do is work backwards. That's our initial thinking. It can change, we can react, adapt, we got this. So let's just simplify the problem, right? So we see this carbon right here was our carbonyl carbon. Now here's where I early in the video I said make cuts that are convenient for you, right? So when we make a cut, we ideally want to siphon off a unit of 3 or a unit of 2, and we can take it directly back to the source. So if we take a look at this, I hope you're seeing that if we make a cut right here and make this a carbon in a Grignard, that's a unit of 1, 2, and 3, right? So that's a good choice. That's a good cut. Yes, we do have a unit of 1, 2, 3, 4, 5 up here, and maybe we will have to do extra work there, but that's a big win to know that this will go directly back to our starting material. So in doing so, right, acidic workup going backwards, we see this is that asterisk carbon right there. That's isopropyl Grignard. And then up here we have, and I drew it a little bit differently, 1, 2, 3, 1, 2, 3, 4, 5, 4, 5, and it's a ketone. This is the carbonyl we attacked. It's 5 carbons. So maybe you're seeing, 5 is a propane and an ethane. So let's just finish this off just so we get a little victory under our belt. So from there, right, and now you can see why those earlier problems are now so good, because we have a bigger fish to fry in this larger problem, but this is old hat by now. So step it back with magnesium to get bromine. It's on a secondary carbon, so when we take it back to propane, we know bromination is the better route to go, because chlorination would give us a hefty bit of product on these primary carbons. So isopropyl Grignard, made, done. Let's tackle this piece right here. I'm going to circle this in red just because it's not quite a mini problem, if I want to call it that. So we know this is a carbonyl. Where do carbonyls come from? With the knowledge we know, they come from oxidation reactions. So to step this ketone back to an alcohol, we could use PCC, we could use Jones, it doesn't matter. PCC just because why not? And we get this alcohol up top. Now maybe, just maybe, so we can see a unit of 2 and a unit of 3. It looks like this was another Grignard reaction, and if you're thinking that, then you are right. If we make a cut right here, this is a unit of 2, that's something we start with, and this is a unit of 3, another thing we start with, so that's a good cut. So if we step this back with acidic workup, protonation, whatever you want to call it, well, look at that. Isopropyl Grignard, which we've already made. So once you've done this, this is already done, you're cool there. Now, we will have to make this ethanal, this 2-carbon aldehyde. But no fear, we know how to do that. It's an aldehyde, so we need to step it back with PCC to get the primary alcohol it came from. And then, primary alcohol, we're going to make that through SN2 once we get a halogen on there. So if we step this back with sodium hydroxide, and again, if you want to flex, go ahead and toss some DMSO in there, whatever. Just getting those polar A product solvents in the back of your mind. We know that we had a good leaving group, chlorine, bromine, doesn't matter really in this situation, so we could go back with chlorine, and that's how this double Grignard is synthesized. Okay, gang, 2 more. I know it's a lot of synthesis, but 2 more, let's do it. Okay, gang, for letter E, we start like always, counting our carbons. Okay, so if we take a look here, we have a 6-membered ring, so that's 6. Then we have propane, that makes 9, and to round off at an even 10, a CH4, methane. So we take a look over here. We see 6, 7, 8, 9, 10. So looks like one of everything in this synthesis. So if we take a look at, we start from the beginning or the end, start at the end and work our way back. We take a look and we see this was our carbonyl carbon in what was a final Grignard reaction, because we see the alcohol, we see stitching together of carbons, evidence of a Grignard. Okay, so with acidic workup, we step it back. Let's make a cut that's convenient for ourselves. So I hope you see that if we make a cut right here, right, we would have 1, 2, 3, 4 carbons up top, not, something that corresponds to our starting material, but maybe we have 4 right here. But I know you see that if we make a cut right there, we directly have our 6-membered ring. That piece right here we take back to our cyclohexane starting material. So in doing so, I hope you see that this 4-carbon ketone is what we see up here, the dot carbon being indicated in both locations, and right here we can see an asterisk carbon, which I'm indicating in both spots. This was our Grignard. So I think you can see we can take care of this pretty easily. Cyclohexyl Grignard, take it one step back with magnesium, and then your choice of bromine or chlorine. I prefer bromine, it's a little bit more tame, it's going to be very selective in this situation where it doesn't really matter, but there you go, that takes care of our Grignard. Now we have this 4-carbon ketone to wrangle. So it doesn't go back directly to anything we start with. Looks like we have another stitching together point. So let's just take it back to something we can digest. So we can either use PCC or Jones in this secondary situation to take the ketone back to a secondary alcohol. It's at this point that we have evidence of another Grignard, so another double Grignard in this problem. So at this position right here, I hope you can see that we have a 3-carbon piece. And again, I'm trying to show you as many 1-carbon either situations where it gets attacked or it is the attacker. If we make a cut right here, which looks so silly, right? There's our 3-carbon piece we can take back to propane, and then we have a 1-carbon piece right here that we can take back to our methane, okay? So, I'm going to do the rest from over here. So I hope you can see when we step this back with workup, we have methyl Grignard, CH3MGBr, attacking propanal, okay? So really quickly, if we step this back with magnesium, that gives us methyl bromide, and then right from CH4 to methyl bromide, little Br2, HV and light. You could use chlorine, but using bromine here, no rhyme or reason. A little bit more tame, maybe a little bit of a reason. So now, we've there we go, try not to ruin my blue marker. We have these 2 to step back. We already did this one, we already did that one. Now for the 3-carbon carbonyl, the aldehyde. Step it back with PCC because we know aldehydes come from oxidizing primary alcohols. And then again, to make this from bare bones propane, we know this is going to be an SN2 thang. We can step it back with sodium hydroxide, DMF, for flex points. And then, we need a good leaving group, right? Remember, we need this. Bromine will not. Bromine will selectively go on the secondary carbon if we use free radical bromination, so we have to do free radical chlorination for a proper good yield in our synthesis. So that is E. To round this worksheet out, we got one more. It's F. It's a little bit of a long one, but I know you're up for it. Let's hit it. Okay, gang. Last synthesis problem, and I apologize if they get a bit wacky on my board. Okay, so if we take a look, right, let's count our carbons. 1, 2, 3, 4, and in our product, 1, 2, 3, 4, 5, 6, 7. Okay, so more than what we have starting with. So if we have 7, I think an easy initial estimation is 2 propanes and 1 methane. Okay, that would give us 7. But as always, let's start at the end, work our way back, and see where it takes us. Okay, so what is interesting is that not only we kind of have something extra going on in our final product here, not only do we just have an alcohol, which is evidence of a Grignard reaction, but we have a ketone, okay? So let's take an initial step back, under the operation of this is a Grignard product, which it is, and let's do Grignard and carbonyl, see where it takes us. This was the carbonyl carbon that was attacked, and we need to make a convenient cut for ourselves, right? Because we're going to be stepping this back after acidic workup. So I hope you're seeing we have this 3-carbon piece up here. One logical cut would be to do this. That would give us 1, 2, 3, 4. It does keep all the kind of the functional groupness in one piece. I think that's a good cut. This will be my Grignard up top. I hope you can see that in stepping it back, I have this 3-carbon piece right here. That's methyl Grignard. And down below, this was a carbonyl, so now we have a ketone. And I like this cut because you can see symmetry, okay? Symmetry is pretty key in this problem. So you can see really, if you had any thoughts or at the very end thinking to yourself, well, one carbon got attacked, what about the other one? I designed this problem specifically to be a bit weird where you have this evidence of a second carbonyl in the product, and it doesn't matter because the piece that gets attacked, it's symmetrical. It doesn't matter if this carbon gets attacked 70% of the time, this one gets attacked 30% of the time. You get the same product either way, okay? So I hope you can see now we have this very simple thing to step back to propane. If we go ahead and just do magnesium, that gives us bromine, right? Bromine's a good choice for the halide we stick on because it's on the secondary carbon, right? It's isopropyl bromide, not propyl bromide. So we can set that back to propane. Grignard is done, but we have work to do. So I hope so now we have this dicarbonyl, right? So we can take these both back to alcohols if we throw in, and I didn't put this on the worksheet, but you could cover yourself by writing, that's just an abbreviation for excess, right? Just as 2 equivalents or more because we have 2 carbons that need to be oxidized, okay? So then, what I did over here was I showed if you throw in water, right, you step this back, you could then stick on a bromine, okay? This, I'm not crazy about this reaction step, but this problem was designed to get your brain really working and trying to solve a synthesis problem. So, right, this would be SN1, no shifts because it's secondary, it's next door neighbors to secondary carbon. Then, if we step, we're here, we could then step this back to just being a Grignard product. If we did free radical bromination, right, that could stick this bromine on. That would give us, obviously, just this initial alcohol beforehand, right? There's nowhere else this bromine will go. That's where it's going to be. Okay, so now in this product, right, this structure right here, I hope you're seeing, okay, we have 4 carbons. This carbon is attached to an alcohol. This is evidence of a Grignard reaction, right? And I can make a convenient cut right here because that leaves me with a CH3 that could be my Grignard, and these 3 carbons right here that would then get attacked. So if we do acidic workup, and follow me, we're going back this way now, we have this piece right here, which would be simple to step back, methyl Grignard, as well as this 3-carbon aldehyde. So I think you can see stepping the methyl Grignard back is trivial. It's magnesium, going back to methyl whatever, bromide, chloride, step that back to CH4. The more interesting part, which we did in the last problem, I think, or one of these problems, is the propanal. Step that back with PCC, right, aldehyde to the primary alcohol. Then, right, primary alcohol, we know that's going to be an SN2 pathway. Step it back with sodium hydroxide, polar protic solvent for bonus points. Then we know this is going to be chlorine, not bromine, because if we did free radical bromination, we get the bromine right here. Stepping it back with chlorine, dropping the markers, walking out because you got the problem right. That's a lot of synthesis for one video. Gang, I don't know about you. I am done for the day. So, thank you for if you're watching this video, that means you have supported jOeCHEM monetarily, and I thank you. I'm floored. I'm so humbled that you're using jOeCHEM as a tool to help you excel in organic chemistry. I hope you're using it now and towards the end of, OCHEM 1 and OCHEM 2. But if anything, I hope to see you all in the next video.